Hello, this is Jack, Caleb, and Travis, and we are presenting today on palladium and copper. Alright, so this is a brief overview of copper, starting with elastic modulus, denoted by E, by the slope of linear section of the stress strain curve. The yield point is a 0.2% offset strain from, and it's where the plastic deformation starts. The tensile strength is the highest portion on the curve, the highest stress on the curve. Ductility, percent elongation, the final length minus initial divided by initial times 100. The area reduction is the original area minus the final area divided by the original area. Resilience under the linear portion of the stress strain curve, so it would just be this formula of sigma squared divided by 2 times the elastic modulus. And then toughness is the total area under the curve. So, starting with the elastic modulus, we use rise over run method to get the elastic modulus. So that would be a higher sigma minus lower sigma divided by a higher epsilon divided by minus lower epsilon. So I took two numbers from the linear section. It did 50.5 megapascals minus 25.3 megapascals divided by 0.000351 minus 0.000117 megapascals to get 107,692 megapascals, which converted over to gigapascals is roughly 108. So to find our yield point, we do a 0.2% offset from the origin of the strain axis. So we do 0.14, which is the total number of, which is the highest strain value, times 0.2% gives us this very small number here, 0.0028. We draw a parallel line to the linear slope and then match it where it intersects with the function, and that gives us about 149 megapascals. The tensile strength is the highest stress on the curve at 263 megapascals. It's just a straight line over from the highest point over onto the stress value. The ductility, percent elongation, and percent area reduction. Percent elongation is the final length minus the original length over the original length times 100. So for the stress strain curve that was found online, the final length was 3,900 millimeters. The original was 3,420 millimeters. Divided by 3,420 millimeters times 100 gave about 14.04%. And then the percent area in reduction is the original area minus the final area divided by final area, original area, times 100. So that was these numbers from the online version. 1.5836 millimeters squared minus 0.3959 millimeters squared divided by 1.5836 millimeters squared times 100. And that gave us about 75%. Then to find resilience is the area under the elastic portion of the curve. So that's given by this formula here. U of R equals sigma squared divided by 2 Young's modulus. So for the sigma value was the highest number at where it intersected. So 149 megapascals squared divided by 2 times 107,000 megapascals squared, but not squared, just 2 times 107,000, gave us 0.103 megapascals. And then the toughness is just the total area under the entire curve. Be typically done by an integral. So this is for question number 7, finding the change in diameter and the change in length for the copper sample. So for this example, we used the percent elongation formula and the percent area reduction formula to find our final and initial lengths. So we were given for copper the original length of 1 meter. We don't know the final length, but we do know the percent elongation at 14.03%. So I rearranged the formula to get what length final equals. Plug in our given values, and that gives us the final length of 1.1403 meters. And then from there, we subtract the original length to get 0.1403 meters. And then finding the diameter, so we were given the radius, so we use the pi r squared formula to get the original area. We don't know our final area, but we know our area reduction of 75%. So we rearrange the formula to get what the final area equals, plug in our given values, and we get 942 centimeters squared for original area. Find out the diameter with the pi r squared formula, and that gives us our final diameter of 17.3205 centimeters. So we subtract that from the original value of 20 centimeters to get 2.68 centimeters difference. So the final width was 2.68 centimeters smaller than the original.
Okay, so the next metal that we looked at was palladium. The first thing that we found was the elastic modulus for palladium. So we got the slope of the elastic or linear region of the stress strain curve, and that turned out to be 73 gigapascals. The next item we looked at was palladium's yield point, and that is where deformation changes from elastic to plastic. So it's the turning point between the linear region and the curved region. And based on the stress strain curve, that was 1525 megapascals. So the next item we looked at was the tensile strength, and that's the highest point on the stress strain curve. And based off the stress strain curve, that was 1561 megapascals. Ductility can be found in two ways, or looked at in two ways: the percent elongation and percent area reduction. As Jack said earlier, percent elongation is kind of measured in the final length minus the original length divided by the original length. The data that we looked at didn't give the initial length and the final length, so we don't have specific numbers for those. But the next item we looked at was resilience, and resilience is measured by looking at the area under the elastic or linear region of the stress strain curve. If you look on the right on the curve, it's shown in the green outline. So the formula for resilience is the stress squared divided by 2 of the elastic modulus. So that was 1525 squared divided by 73,000 times 2, and that turned out to be 15.92 megapascals for the resilience. So after resilience, we were asked to look at toughness. Again, we didn't have a formula to really calculate the toughness, but we know that the area under the elastic and the plastic region, so the area under the entire curve, shows what the toughness of palladium is, and that's outlined in red on the graph on the right hand side of the screen. So for question 7 of this project, we needed to calculate the change in length and the change in width of a cylindrical specimen that's 1 meter long and 20 centimeters in diameter. So we found this by using the formula force times length divided by area times modulus of elasticity. As you can see, we did 4,000 newtons, which was the force, multiplied by 1,000 millimeters, which was the original length of the specimen, divided by 31,416 millimeters squared, which was the surface area of the cross-sectional area of the specimen, and then multiplied by 73,000 newtons per millimeter squared, which was the modulus of elasticity for palladium. Based on this formula, the increase in length is 0.002 millimeters. So using that change in length and Poisson's ratio of palladium, which is 0.39, the diameter decrease can be calculated by multiplying the Poisson's ratio by the length increase divided by the original length, which is 0.39 times 0.002 millimeters divided by 1,000 millimeters, and that gave us a diameter decrease of 7.8 times 10 to the negative 7 millimeters. I'll pass things over to Caleb to talk about our alloy.
For our alloy, we chose brass, which is a copper alloy, and the stress strain curve that I was able to find gives us the strain and stress for brass. And in the bottom left, it shows the elastic module, which I got was 110 gigapascals, the yield point, the yield strength, which was 200 megapascals, the tensile strength was 430 megapascals, the percent elongation and percent reduction of area was 35% and 8%. The resilience that I got was 0.409 megajoules per meter cubed, and the toughness that I found was 70 megapascals times meter divided by 2. The way that I was able to get the elastic modulus is using the equation E equals sigma times epsilon. I was able to find the yield point through the graph, and the tensile strength I was able to find using the force applied divided by the area under the curve, which got us 430 megapascals. And then after that, I was able to get the percent elongation and percent reduction of area by using the equations the length final minus the length initial divided by the length initial, which gave me the percent elongation, and the area initial minus the area final divided by the area initial, which gave me the reduction of area. I was able to get the resilience by using the formula 1/2 times the yield strength squared divided by Young's modulus, which got us 0.409. And then I was able to find the toughness from the source that I had found.